I'm going to talk about HamSCI and the 2023 and 2024 solar eclipses. How many people here know that we have these solar eclipses coming up over the next year? Okay, great. Seems like everyone knows that. How many people here participated in the last solar eclipse QSO party? Got a couple hands, great. Okay, so I started and lead the Ham Radio Sciences Investigation, also known as HamSCI. So this is a collective or a group that allows university researchers to collaborate with the amateur radio community in scientific investigations. And I thought, I've got a microphone. You're welcome. How's that? All right. So I started out in ham radio. I got interested in it when I was about middle school age, and that's actually why I became a professional ionospheric researcher. So I thought it would be really interesting to join the two groups together. So I'm sure everyone here knows about this, the ionosphere. It's generated primarily by photoionization. So when you have the sun during the day, you have a stronger, more complicated ionosphere with the D region, the E region, F1 and F2 regions. At night, when the sun goes away, photoionization stops and recombination takes over, and the ionosphere becomes less dense and it becomes simpler. So what happens if you have a situation where the moon goes in front of the sun and you get the shadow of the moon on the earth? It's kind of like temporary night conditions, and so you get a change in the ionospheric propagation. And so here, this is a ray trace model illustrating this. It illustrates we've calculated the propagation path on 14 megahertz from AA2MF in Florida over to WE9 Victor in Wisconsin. And Dr. Joe Huba from Syntec Technologies, he ran a physics-based model called CME3 that had the eclipse, the 2017 eclipse in there. And so you can see that when the eclipse comes on, the ionospheric densities decrease, the band shuts down because the rays don't get refracted back to Earth and they escape into space. So this is showing how you get refraction as a function of electron density. So of course, this is what allows us as amateur radio operators to communicate with each other. This is also useful from a scientific perspective because it lets us remote sense the ionosphere. If you are at a receiver over here, if you see any changes in the signal from what was originally transmitted, or if the signal simply is not there, you know something about the propagation path between the transmitter and the receiver. Often we assume at the midpoint. So that's where the remote sensing comes in. It's also useful to know that refraction is a function of frequency too. So if you have two equivalent ionospheres, which we have here, if you're operating at a higher frequency, say 15 megahertz, you can maybe do one hop, will get you 1,500 kilometers ground distance. If you go down to 10 megahertz, you can go 1,500 kilometers and maybe two hops. Of course, that will depend on what particular ionosphere you're using. So in this particular case, I'm using an international reference ionosphere model from November of 2016 as my case, going from Virginia. So in 2017, there was a total solar eclipse, and I organized, along with the other people in HamSCI, an event called the Solar Eclipse QSO Party to look at how the eclipse affected radio propagation and the ionosphere. So let's review some of those results. So in 2017, the eclipse started in the northwest United States at 1604 UT, and then partial eclipse ended in the southeast United States at 2013 UT. It went diagonally across. And we really care about eclipses because they really serve as controlled experiments in ionospheric and space physics. So there's certain things like dawn, dusk, and the seasons where we do know how much solar energy is going to be put into the upper atmosphere. But aside from those cases, there aren't many other cases where we know this. So for instance, solar flares, geomagnetic storms, other types of space weather, we simply can't predict what the inputs to the system are going to be. But solar eclipses fall into that category of things where we can calculate where the shadow of the moon is going to be, what's going to happen. And so this is a very useful controlled experiment. So for HamSCI, we had some questions. Can we use HF ham radio communications to observe eclipse effects on the ionosphere? Can we use data model comparisons to better understand the ham radio data, to calibrate or constrain the model? And so we ran this solar eclipse QSO party. We ran it on August 21st, 2017 from 1400 to 2200 UTC. And we made it contest-like. I wanted it to be as much like a ham radio contest as possible. So we got 2 points for CW QSOs, 2 points for digital QSOs. You got 1 point for phone. We tried to incentivize the CW and the digital because those could be automatically observed by the reverse beacon network, PSK reporter, WhisperNet, those networks, and that was our primary source of data. We also wanted people to talk across as many paths as possible. So we had a multiplier of by grid squares. I'd say the SEQP was quite successful. We successfully processed 570 logs, and we had almost 30,000 QSOs in there. From the automated networks, we had over 600,000 spots from the RBN, over 600,000 spots from WhisperNet, and over 1.2 million spots from PSK Reporter. So I really just had time to look at the RBN data, and so that's what you see over here. These are all of the RBN spots over the continental United States from the 2017 SEQP. So if you were a CW operator during the 2017 SEQP, you should be able to find your dot on this map. The little black dots are the CW stations, the transmitters. The blue stars are the locations of the reverse beacon network automated CW skimmers. And the colored spots in between, those are the locations of the midpoints halfway between each transmitter and each receiver for every spot. And we're using the midpoints here again because we're assuming that's one hop propagation and that's where the ionosphere is affecting the radio signal. I have it color-coded by maximum value of the eclipse, so you can see the path of totality right here in the data. So if you look at it this way, we can plot the observations on top. I have observations on top, and I have the model on the bottom. So the way you read this, on the x-axis is time relative to maximum eclipse. Right in the middle is the maximum eclipse. All the way to the left is an hour and a half before the maximum eclipse. All the way to the right is an hour and a half after the maximum eclipse. The y-axis shows the distance between the transmitters and the receivers going from 0 to 3,000 kilometers. And the colors shows the spot density of the RBN spots for that particular time and location. So we can see that starting an hour and a half before the eclipse, 20 meters, 14 megahertz was wide open if you wanted to talk distances between 1,000 to 2,000 kilometers. And it stayed that way up until about an hour to 45 minutes before the eclipse. And that's when you started having the partial eclipse cause the band to shut down. As you went into maximum eclipse in totality, the band was really, the propagation conditions tanked. After the eclipse, you started to see recovery. The band started to approach what it was before, but never quite made it back. So we were able to model this using that same SAMI 3 model I showed you before. That one ray trace that I showed you, we did that for every single RBN receiver to a grid of theoretical transmitter locations over the entire United States on a 3-minute cadence for 4 different bands for the duration of the SEQP. And so here's the 14 megahertz results. You can see that it matches quite well. Not perfectly, but very well. So here again you have the band is open before the eclipse, shuts down during the eclipse and then opens back up. There's not as much spread in range as there is in real life. We modeled more than just the 14 megahertz. We did 14, 7, 3.5, and 1.8. And I found that you needed to split the model results up into E region refractions and F region refractions. So 14 megahertz agreed very well with the E region model, which was perhaps a little bit surprising. I would have guessed that the 14 megahertz signals would have been refracting off of the F region during the SCQP, but that really isn't what we found. We found that was mostly low angle E region refraction on 14 megahertz. You can see here that 7, 3.5, and 1.8 megahertz, the observations over on the left do not agree well with the model. However, if we change the model results to only look at the F region refractions, you can see much better agreement, particularly at 7 and 3.5 megahertz. So the 40 meters goes long during the eclipse, and 3.5 megahertz opens up as the D region absorption goes away. So what's going on for the 2023 and 2024 eclipses? Well, we have two different eclipses coming up. The first one is October 14th, 2023, and that is an annular eclipse that again is going to start in the northwest United States and go down to the southeast. And then April 8th, 2024 is going to be a total solar eclipse starting from the southwest US and then leaving up in Maine. So what's the difference between an annular and a total solar eclipse? A total solar eclipse is where the moon is a little bit closer to Earth and the moon's disk completely covers the solar disk. And then all you can see, all you can see is the corona around the moon during totality. An annular eclipse is when the moon is a little bit farther away from the Earth and it doesn't completely cover the solar disk, but it still lines up right in the middle. And you end up with this ring of annularity of the sun around the moon. If you are not in the path of totality or the path of annularity, but you're going to be in the United States, you will probably see at least a partial eclipse where the moon's disk just partially covers the sun. So I made this animation using Python and AstroPy and Matplotlib that shows the paths of the eclipses. So here's October 14th, 2023. This is the annular eclipse. And this is done at ionospheric heights at 300 kilometers altitude. I think one thing that is neat looking at this animation is that it's not just the United States and Canada that's getting this. It's going all through Mexico and down through South America as well. So when we have the SCQP, we're going to encourage the South American amateurs to participate as well. So we'll try to make this a larger SCQP than in the past. Over here, we have the path of the total solar eclipse. So this will be April 8th, 2024. So I gave these results to Dr. Joseph Huba again, and he was able to do a SAMI 3 ionospheric model prediction once more. So far, we just have it for the annular eclipse in October, but this will show you a prediction of how the eclipse is going to affect the ionosphere. This is a differential total electron content map. So what the model is showing is it's just adding up the total number of electrons from the ground up into space, and then the differential part is he's subtracting the eclipsed result from the non-eclipsed result, so you can see the difference. Here we go. Do you think that's going to affect your radio propagation? Play that one more time. So I have to say, Frank Donovan, LPL, he really set me up well here because he was talking about that ionospheric equatorial fountain effect and the equatorial ionospheric crests. You can see that right here. These are because of that particular effect, that splitting there. The other thing that's interesting, you see this little feature over here. This is an equatorial plasma bubble that only shows up because of this annular eclipse. So when Joe ran the model without the eclipse, you don't see this bubble. So this is an interesting prediction. So these eclipses are a really big deal for us. So we're going to not just have a single solar eclipse QSO party. HamSCI is running a whole festivals of ionospheric eclipse science. So what do we have in that? Well, we do have our traditional solar eclipse QSO party. We're also having something called the Gladstone Signal Spotting Challenge, or the GSSC. And this is a contest for people who are actually running the skimmers. So the more people you spot, the more points you get. This is also the category or the contest where if you like running Whisper or FST4W, you can participate in this. Then we have some events, or I should say experiments, that are not contests. We have the TDOA, time difference, it should say difference of arrival event, or time difference of arrival experiment. And we have the GRAPE HF Doppler experiment. And we also have a few more. So I'll talk about each of those now. Let's start with the science questions. These are the science questions for the upcoming Solar Eclipse QSO party and the Gladstone Signal Spotting Challenge. So can the annular eclipse be observed in HF communications? How large is the disturbance? How long before and after maximum eclipse are eclipse effects observed? Is an onset recovery asymmetry observed? Will the results again suggest the E layer propagation for 14 megahertz and F layer for 1.8 to 7 megahertz? How similar are the eclipse effects to dawn and dusk? Gray line. So these will be taking their place on, of course, the eclipse days. They're going to last about 10 hours each. So we have an update to the rules, the Solar Eclipse QSO Party 2.0. We're going to take the best concepts from the 2017 event, and we're going to update those rules, etc. You can find all the latest rules and details at hamsci.org/eclipse. For the SEQP, we're encouraging all different varieties of modes. Any digital mode you want, CW and phone. For the bands, you need to stay on the contest bands only, so no WARC bands. And for CW and sideband, you can call CQ SEQP on the 38s. For digital modes, you want to use the usual activities centers, but you can spread out if it gets a little crowded. So the standard exchange, now this one really got the Contest University people laughing a bit the other day. We're asking people to do an accurate signal report for the contest. Yeah, I thought that's what you would say. But as I said to them, I'm not really expecting for me personally, to get any real scientific value out of it. It's very subjective. But it's really more for you, that you might be able to track and kind of appreciate the changes in the propagation in real time. So accurate signal reports, 4-character grid square exchange. If you miss any information, simply ask for it again. For the scoring, you multiply the QSO points times the number of multipliers plus the bonus points. So 2 points for CW and digital, 1 point for every sideband QSO. You get multipliers, 4-character grid squares counted once per band. And the last rule here, again, is different from normal contests. Dupes are allowed every 10 minutes. And the idea here is that you're testing the same propagation path again and again and seeing how it changes with time. So the Gladstone Signal Spotting Challenge, this is a contest for people who like running skimmers or operating the beacon modes like Whisper or FST4W. And this challenge is named after Philip Gladstone, N1DQ, the founder and operator of PSK Reporter. So the scoring for here is you get 1 point for every spot received. We're trying to encourage the adoption of FST4W-120, which has some additional advantages in terms of being able to measure spectral width and things like that. So you get a 1.25 multiplier for that. You get 1.1 multiplier for uploading information about your station design, and 1.05 for uploading some information about photos of your station. So the SEQP and the Gladstone Signal Spotting Challenge are a bit more of random events. The next thing I'm going to talk to you about are experiments that are a little bit more controlled, a little bit more well designed or intentionally designed, make use of more precision measurements. So the first one involves the HamSCI Personal Space Weather Station project. So we have an NSF-funded Eclipse experiment for that. So again, what is the HamSCI Personal Space Weather Station? This is a project to develop a low-cost, ground-based receiver system that can take measurements about the ionosphere and its connection to space. And so the typical personal space weather station has at its core a radio, a software-defined radio. That radio needs to have a GPS-disciplined oscillator, so very stable frequency reference and clock. That goes into a computer. That computer can also take in ground magnetometer measurements because we know that ground magnetometer measurements give us information about the currents flowing overhead in the ionosphere and space, which can also give us information about how propagation is at a current point in time. We can also have a VLF receiver, and then this all goes out to the internet to a public database. We have many different institutions and organizations participating in this, including the University of Scranton. There it is, Jim, the University of Scranton, okay, where I'm from. Also University of Alabama, Case Western Reserve, NJIT, Tapper, and this is supported by NSF and ARDC. So we have a few different systems here. We've got the low-cost GRAPE system, which I'll be talking quite a bit more about shortly. The low-cost GRAPE system is a system that's designed to monitor the Doppler shifts of signal received from a standard station such as WWV or CHU. Now, you'd expect those stations have atomic clock accuracy and stability, so you expect that if you're listening to those carrier signals at, say, like 10 megahertz, it would be dead on and it wouldn't change. But if you have a very stable receiver, you'll find that that's not true. You'll find that the frequency dances around a bit, and that's due to variations in the ionosphere. We also have the Tangerine SDR, which you can learn more about at the Tapper booth. I mentioned that part of the personal space weather station is this VLF Whistler catcher module, and this is a system developed by Jonathan Rizzo, and this listens to signals way down around 100 kilohertz. You can see Jonathan standing next to the receive antenna out there, and here you're able to listen to we're taking a little detour away from the Eclipse for a minute. Here you're able to listen to some other interesting phenomena. So there's something called whistlers. Let's see if this works. So you hear that whew. So that is what whistlers, where whistlers come from is if you have lightning in, say, the polar regions, that lightning can release broadband electromagnetic energy, which can then go out into the magnetosphere, propagate along magnetic field lines, and then come back in to the Earth in the other hemisphere. And along the way, that energy experiences frequency dispersion, which is why you get this whistler here. Play that one more time. So this is something that was observed near Scranton with that particular system. You also can see things called dawn chorus waves. So here's observations of dawn chorus waves. These again come from interactions that are happening out in the magnetosphere. So here are ones that we observed in Springbrook, Pennsylvania, and here are ones we observed in Forest, Virginia. And then here's the magnetometer developed by Tapper and also by NJIT. And if you want to buy a ground magnetometer, you can actually go over to the Tapper booth at this Hamvention, and they will sell you one. But I want to go back to the GRAPE low-cost personal space weather station, because this is the one that is going to be used for studying the upcoming eclipse. So again, you have WWV over here, you have your receiver over here, and as the signal goes up, as the path length, as the ionosphere changes, the path length can increase and decrease with time, and that can cause variations on the received signal that this can observe. We have two different versions of the GRAPE. We have the GRAPE version 1.12, which is available now. This is a single frequency system. You build it yourself. You build a little board that looks like this, and then you attach it to a Leo Bodner GPS discipline oscillator into a Raspberry Pi, and you are on the air and making measurements. We also have the GRAPE version 2, which will be able to do 3 frequencies simultaneously. It will be pre-assembled. We have the prototypes are currently being built right now, so we hope to have those out soon. So here's some examples of GRAPE type measurements during the last solar eclipse. So these measurements were made by WA9VNJ, who's now a silent key, on 10 megahertz listening to WWV. So WWV is out here near Fort Collins, Colorado. WA9VNJ was over here near Milwaukee. And the eclipse path was going this way. And what he observed, this is what happened the day before the eclipse. So this is a control day. The red dotted line here is showing the solar elevation angle. So here's noon right in the middle. Over here is dawn, and over here is dusk. So as the sun rises, the ionosphere is building up, the path lengths, refraction is increasing, the path lengths are getting shorter. With time, you're seeing positive Doppler shifts associated with dawn. In the evening, as the ionosphere starts to recombine, you have the ionosphere thin out, refraction, path lengths increase, refraction decreases, you have negative Doppler shifts. So you see that over there. Look at this flash right here, sudden increase in Doppler. Anyone have any idea what that is? Why do we see that? That's because of a solar flare. So you have a solar flare there, you got a sudden burst of X-ray energy, causes sudden increase in D-region ionization, and you see this big flash there. So that's the day before the eclipse. The day of the eclipse is down below. Now this dotted black line shows when there was maximum eclipse, and so you can see here you still have the morning positive Doppler shifts, the evening negative Doppler shifts, and then as the eclipse comes on, you have negative Doppler shifts similar to evening. And as the eclipse goes away, you have positive Doppler shifts similar to morning. And these Doppler shifts are only on the order of, say, like, 0.1, 0.2 hertz. So these are very fine measurements, and that's why you need that GPS disciplined oscillator. You notice there's also a lot of variation in these measurements here. It's very noisy. So it turns out that you really can't effectively just make the measurement, say, once a second or one frequency measurement for each period of time. You really need to look at a spectrum. So this is how the GRAPEs have been recording the measurements so far. We're going to be transitioning to a system where we're recording a spectrum of data, so we're able to better capture the physics that's actually happening with these Doppler shifts. So here's an example of that. You can see it's a very complex signal. This is data recorded at 5 megahertz by Bill Engel, key AB4EJ in Alabama, listening to WWV. You can see through the night all this variation here. In the morning, the F region is rising up here, and then E region kicks in right over here. We have even more examples of this taken by Steve Serwin, WA5FRF, out of Mica, Texas. And he gives us 5 megahertz measurements, 5 of them here at dawn. So this is positive excursions during sunrise, and then 5 of them negative excursions during sundown, during dusk. And they're really beautiful figures to look at. You can see that no one dawn and no two dawns and no two dusks are exactly alike. There's a lot of variation here, a lot of interesting physics, and it really affects the radios in an interesting manner. You see this, what we call propagation mode splitting. So I'll show you a little bit more about that in a little bit, but you can see every single one of these is a little bit different. And that's one of the things we're interested in looking at during the upcoming eclipse. You know, do we see this sort of mode splitting during the eclipses, and how does that look? Here's another example of grape data. This is using just the single frequency measurements, but this is looking at almost 2 years of observations. And this was taken at 10 megahertz from near Cleveland, Ohio by John Gibbons, N8OBJ. John's the Case Western engineer who designed the whole grape system. So on the x-axis here, you have almost 2 years of observations starting from August, September 2010, going up through April 2022. And then on the y-axis is local time, midpoint local time. So midnight is at the bottom and the top, and local noon is right in the middle. Excuse me. And here you can see the blues are positive Doppler shifts, and the reds are negative Doppler shifts. So just like we saw the positive Doppler shifts at dawn in the previous plot, you see that here. Similarly, we saw the negative Doppler shifts at dusk in the earlier plot. You see that here over the entire 2 years. But not only do you see that, you also see the seasonal variations. You see that during the summer you have more hours of daylight, and then in the winter you have shorter days and longer nights. And so you can see that seasonal pattern very nicely in these observations. So as part of this new NSF-funded program, we are working on deploying a network of these across the entire continental United States. So all of the black dots are locations where we're intending on deploying these receivers. And you can see the path of the annular eclipse, the path of the total solar eclipse, and then you can also see locations of WWV and the Canadian counterpart CHU. And the colored dots here are the midpoints between the receiver locations and the transmitter locations for each of these. So you can see approximately where our sampling locations are. So I've got one more experiment I want to talk to you about, and that's something called the time difference of arrival experiment. And this particular experiment is for hams who both want to transmit and they also want to do so in an experiment that's a little bit more again, a little bit more purposeful than, say, a little bit of the randomness of the SEQP contest. So the time difference of arrival experiment, here we're using a chirp waveform. It's possible to get relative path measurements even without a GPS discipline oscillator. So in this eclipse time difference of arrival event, we're asking pairs of stations to team up in small groups to systematically transmit and receive customized chirp waveforms to make these measurements. So this effort is being led primarily by Steve Serwin. This is really his idea, WA5FRF. And so you can see him over here. And then I also have Dr. Christina Collins, who just finished her PhD. She's graduating actually this week from Case Western. She was our great PhD student. She's also helping with the waveform development and some of the work here as well. So what are the science questions here? So we ask, what is the observed change in effective F2 ionization layer height caused by the momentary blockage of solar radiation? And is symmetry observed in layer height changes when comparing before eclipse and after eclipse layer heights? So how does this work? So the time difference of arrival between 1 and 2 hop modes can be used to deduce layer height. So here's an example of 1 and 2 hop modes. So your transmitter's over here. So 1 hop goes this way to the receiver. 2 hop off of the same ionospheric layer will go up, then down to the Earth, and then you'll get a second hop that way. So clearly it's going to take longer for the 2 hop mode to get there than the 1 hop mode, and then when the signal is received there, it's going to be a sum of those 2 signals. So in effect, this is a multipath situation. You can use this. Here's a chart showing the path lengths versus the time of flights for the 3 different hop modes. This is showing that you have a 1-hop mode, 2-hop mode, and 3-hop mode curve. And if you were to look in the E region, there's actually not much difference in the time delay between the different modes. So it's hard to tell the difference. But when you get up to the F region, the difference is big enough that it starts to be measurable. So we're going to take advantage of that fact. So what we're going to do is we're going to use an audio frequency chirp that can be used to sense the time difference of arrival between different simultaneous multipath signals. And so here you're seeing 200 hertz per millisecond chirps where the bottom one is delayed 1 millisecond relative to the top one. The bottom one is also 3 dB lower in amplitude. If you were to add these two together, that would basically be simulating what you'd see at the receiver. And so then you'd get this pattern over here, and you can see the summation produces a waveform with a beat note period of 10 milliseconds. So using this, you're able to calculate the difference frequency, and you're also ultimately able to calculate the time difference of arrival. So Steve has been working with another ham, Paul N5DUP, about 300 kilometers north of Steve's location in Mica, Texas, and they have been doing this to test out the time difference of arrival experiments. They've been using the 60 meter and the 75 meter band here, and they were chosen because there's a high likelihood of simultaneous 1 and 2 hop propagation modes. And so they were able to successfully measure these results, and they were able to get these approximate heights for the different ionospheric layers. So it seems to be working. We can look at this a little bit more closely. I'm showing you something slightly different here. This is an example of Steve Serwin listening to WWV again and showing the different Doppler shifts from WWV. And here you can see that this one here is associated with E region. So you can translate that to an E region layer height estimation. This trace here is associated with single hop F mode propagation. That's this blue one over here. And this outer trace is associated with a 2-hop F region propagation, which is this over here. And it's also interesting to do this simultaneously on multiple different frequencies, say like 2.5, 5, and 10 megahertz. This sort of multi-mode splitting occurs most reliably below 10 megahertz, so therefore the TDOA experiment for the Eclipse is going to be concentrated on 40, 75, and 160 meters. So how do you participate if you want to? You can go to HamSCI.org and you can click on the Eclipse Festivals of Eclipse Ionospheric Science banner, and then you can just click the next link to TDOA, or you can go here directly, and then you can register. And then you'll eventually be assigned to a pair or a small group of hams. And you'll be asked to generate a custom chirp waveform that you'll be transmitting through your transceiver. And you'll generate this custom chirp waveform using an online Jupyter notebook. Stations will take turns sending and receiving the custom chirp waveforms every 6 to 10 minutes for at least 2 hours throughout the eclipse. And they'll return the recordings to the HamSCI website for analysis. And if you want to help with the analysis yourself, you're welcome to do so too. And if you have any problems with any of the steps in here, we'll be happy to help you out. We have different telecons that you can come join in on and participate, and people can help you with these things. Here's an example of what the custom waveform looks like. So it does include a CWID and a grid square, and this is the notebook that you used to generate that. And they're going to do a dry run of this approximately 1 month before the actual eclipse, and that will give everyone a chance to check out their hardware, software, make adjustments well in advance. And so right now we're proposing September 16th for that test run, but we will, if you register, you'll be notified well in advance. So if you'd like to get involved more, we would love to have you. As you can see, we have many different activities you can participate in. You can also join our community. We have a Google group. You go to hamsci.org. You can find this big blue button, and we now have over 800 members, so you can join the HamSCI Google group there. We also have a number of specialized email lists and telecons. So if you're interested in, say, the HamSCI Grape project, there's a Google group for that. We have these weekly Zoom telecons. We have the Tangerine Development Telecon on Monday nights. We have the Grape Telecon Thursday mornings. And we have the Solar Eclipse QSO Party Telecon Thursday afternoons. If you go to the HamSCI website, you click that blue button again, you'll be taken to a Get Involved page, which will have the links to all of these telecons on here. You click that link, the Zoom will pop right up, and you'll be able to talk to us in person at these times. And it's really great because if you have any questions or questions about the project, you can talk to us that way. But also, if you're interested in, if you have comments on how to make it better, or if you'd like to do things like help out on the SCQP scoring committee, or learn how to do data analysis and help with the data analysis, or come up with your own suggestion, you can work with the team directly there. Finally, I have many different people I have to thank who really helped make HamSCI possible. But one person I really want to thank this particular trip is Gary McKeaton, AF8A. He's our new HamSCI volunteer ham radio community coordinator. So he's helping me to manage all of these projects, get the word out. So if you email us, you might hear from him. You can go talk to him at the booth. And finally, you can visit us in our booth. The HamSCI booth is 5008. We're right next to Tapper, or with Tapper, and you can see us all pictured there from last year. If you want to be in this picture this year, 9:30 a.m. tomorrow morning, we're going to take the group photo. We have booth talks at the Yoda booth, both today and tomorrow, and we have our own HamSCI forum tomorrow at 2:50 p.m. in room 4. So finally, I'd like to thank all of our sponsors, the National Science Foundation, NASA, ARDC, and most importantly, the amateur radio community, because without you, none of this would be possible. Thank you, Tim.